Now, a special case of rotation about a fixed axis that we often come across as engineers and we come across in mechanics is gears and gear ratios. They're really important mechanisms for us. So we often find that this is going to be an issue with those, and there are some good equations and some relationships in our linear and angular kinematics that we can use to relate these gears and gear ratios. So, for example, if we've got like our little gear, you'll have to play along with me here in my little gears. I don't have a gear like emoji. But if I have a pair of gears here, and I'll make this one yellow, I guess. So let's call this gear A and gear B. If I've got gear A and gear B here, and they're both rotating, right? So gear A is rotating clockwise, and we're going to say gear B is rotating counterclockwise. So that those little tips of their spikes there, their little teeth, are going to intersect and they're going to turn kind of around each other. What we're going to see with our linear relationships here is that our velocities of these two gears is going to be the same. So the velocity of this tooth as it travels down is actually going to be the same as the velocity of this tooth, where these two teeth kind of intersect with each other. Right, this point where they touch each other. Those velocities are actually the same. So our VA is going to equal VB. And likewise, those accelerations in that tangential direction are also going to be the same. Right, so with this guy, you're going to have your tangential acceleration of A is going to be the same as your tangential acceleration of B. What's different between them is that the normal acceleration is not the same. And that's typically because we have gears that have teeths. Gears, their teeth tend to intersect, and we have typically different sizes of gears. They have a different radius. So our radius of A is likely going to be different than our radius of B, which would look a little better if they were a little more circular. But those radii are typically going to be different. And so their normal accelerations are not going to be equal. So this is one way that we can kind of look at these gears in analyzing their linear relationships, right? So their velocities and tangential accelerations are going to be the same, but their normal acceleration will not be. We can analyze it with those linear relationships, or we can use our angular kinematics that we've discussed. And those have a special kind of relationship, where we can take for either our angular position, angular velocity, or angular acceleration, for any of those, we can create a relationship between the gears. So our angular position of that like little point A there, for gear A times the radius of gear A equals the angular position of B times the radius of B. And this works the exact same all the way down through our velocity and acceleration. So our angular velocity of A times the radius of A equals angular velocity of B times radius of B. And our angular acceleration of A times radius of A equals angular acceleration of B times radius of B. And sometimes it may be necessary to go back and forth between these relationships, between our linear and our angular kinematics here. But these gears are a special case. They're an important case that we often come across. So we'll go ahead and use these guidelines to go ahead and work through an example. Alright, so thankfully for this example, I've got an actual picture of some gears here that'll probably be a little bit easier to visualize and work with. And in this example, we've got a motor that gives gear A, and that's the gear on our left, that smaller gear. A motor gives gear A an angular acceleration of alpha equals 4t cubed radians per second squared, where t is in seconds. If the gear is initially turning at an angular acceleration omega equals 20 radians per second, determine the angular velocity of gear B when t equals 2 seconds. So a few things that we're given here. We know we're going to be working with a gear problem, hence the image there. And we are given that our angular acceleration of gear A is 4t cubed radians per second squared. We are given that the initial acceleration, initial angular velocity of gear A is 20 radians per second. And we want to find the angular velocity of gear B at t equals 2 seconds. And then looking at our image over here, we're also given that the radius of gear A is 0.05 meters, and the radius of gear B is 0.15 meters. So, bearing in mind that we know we're going to have a gear problem, we have some of these relationships that we can work with, and we know we're going to be finding that angular velocity of B. So I think a good place to start would be just writing down some of those relationships that we might be able to use. So we're finding that angular acceleration of B. I know I can use that ratio of angular velocity of A times RA equals angular velocity of B times RB. But don't fall into the trap of just putting in this angular velocity that we were given, because that's not our angular velocity at 2 seconds. Right? We're going to need to find that angular velocity at A at 2 seconds first before we can plug into this relationship. Let's go ahead and do that. We know we want to find our omega A, right? Angular velocity of A. Our acceleration's not constant, it's 4t cubed. So we know we're probably going to have to take an integral here, where we have this relationship between our angular acceleration is d omega over dt. And so if I rearrange this, let me move this guy out of the way. I can rearrange this so that I get alpha dt equals d omega. And if I integrate those, I might swap these around. So I'm going to integrate our, I don't want to confuse you, I'll just leave it. We're integrating our alpha dt. So our time, we're going to start at 0 and go to 2. So 0 to 2 seconds for alpha, which was 4t cubed. 4t cubed dt equals the integral of our d omega. And so our omega is going from an initial omega of that 20 radians per second to the final omega A. And this omega A is what we need for this relationship here. So that's the guy we're trying to find. D omega. When I take this integral, I'm going to get t to the 4th from 0 to 2 equals omega A minus 20. So here I get 2 to the 4th plus 20 gives me omega A, which is an angular velocity of 36 radians per second at t equals 2 seconds. So this value is the value that's going to go into my relationship up here. And now I can plug in all the values that I know for that. So that's my 36 radians per second times the radius of A, 0.05, equals angular velocity of B times the radius of B, which is 0.15 meters. And if I plug that into a calculator, I get my angular velocity of B is 12 radians per second. So we can see this kind of makes sense. Our gears, if we look at them, our A was 0.5 meters, or sorry, 0.05 meters in radius, and then B was 0.15, so B is triple the size of A. So when we look at those angular velocities, B is triple the size of A and is 1/3 the angular velocity of A. So those gear ratios are really helpful in figuring out how those velocities, accelerations, how they change from gear to gear, as is going to be very important for any mechanical engineers, for really any mechanics problems where we have motion. It's a super, super useful tool for us to have, understanding how these gear ratios work.